Welcome to Simple Circuits 3. You can use this video to review some things that we already know. We'll also just get more practice at doing the simple measurements and simple builds on circuits and so on. For this simple circuit, we have the batteries in series aiding, and then we have a push button which will open the path. So obviously no current will flow when that path is open. There is no path when the push button's up. When you press it, of course, it completes the circuit, and now there is a path for current, and it'll flow through the push button, through the lamp, and through this resistor. So this is a simple series circuit, and we will develop the whole theory behind series circuits more fully in the next chapter, but we'll get a little start on it here. It's a simple series circuit. One thing you can say about series circuits, there is only one path. So there is only one current, which means current is the same everywhere. And maybe a little bit of help if you have trouble visualizing that. Do remember that the wire is not like an empty pipe. It's full of electrons, full of charge. And for charge to move here, it has to move here. So current moves everywhere. If a pipe were full of water and you started flow here, you would also start flow here. It's not like it would start and work its way down through an empty pipe. It's not like that. It's a full pipe. So already, and any movement here is also going to cause movement here. It has to move all together. So that might help with visualization. But there is only one path is another way people like to think of it, just to remind themselves that how could there be more than one current? There's only one path, so it's the same everywhere. Okay. Let's wire it up and then practice taking some measurements with our DMM. So we've got this first connection here that we need to make, maybe between the batteries. That's the series aiding part. Okay, and I can do that very quickly and easily with a jumper. Now I've got the batteries in series aiding, right? Okay. They're both pushing the same direction. Next thing I'm looking at is maybe this connection. I just need to bring a push button into play here. So I can pick a spot on the breadboard anywhere I want and just put that, once I have the push button down, then I have to remember which nodes it's on, of course, but I can see the positive side of my voltage source comes to one side of the push button. There, that's done. And the other side of my push button goes to a lamp. So I got to drop a lamp on here somewhere. Can do that. And now I have this, what you would call the switched voltage is on the other side of that push button. And I can bring that right to a lamp, right? Just like that, just like so. I can scoot this down a little bit if you want to see those wires, right? Okay. Well, the other side of the lamp, obviously, I think, let's see, we finished this. Notice how I'm doing it one connection at a time. It makes life easy, doesn't it? I'm not trying to picture the whole thing at once. Although, I mean, granted, on a simple circuit like this, it wouldn't necessarily have to talk through it one connection at a time, I realize. But not a bad habit when you get to a more complex schematic. Okay, other side of the lamp. Well, I got to get a resistor here. So I can pick a resistor, and you know what? I'm going to pick a 10 ohm resistor. And if you remember, 10 ohms, you can measure it with your ohm meter, of course. That wouldn't be bad to do that, huh? You want to try it? Okay, let me get the ohm meter out here. Hold on a second. So I switched to my mini grabber leads. I like those for checking components. And here we have my resistor. I'm picking a 10 ohm resistor. So if you remember, we've got, I've got it backwards here for you. Let me flip that just so you can see the color bands as a simple review. We'll do a whole thing on color bands probably this week. What do I have? Brown, black, black. So 1, 0, 0. And the third 0 is a multiplier, 10 to the 0. It's a 10 ohm resistor. It's showing up as pretty close, huh? 10 ohms. It does vary. Don't worry about that. Part of that's the accuracy of our meter. Part of that's maybe the contact resistance, the oxide that might be on the leads. So, I'm going to weigh that one in at 10 ohms. It seems to be not a bad approximation. I mean, I know this is the part that you might have a hard time knowing what to do. So 10 ohms seems pretty good. of course, notice I have the meter set for ohms here, and it shows up here. Well, it shows up as auto ranging. That's what you want. Right now it's showing overload because I don't have the leads connected to anything. I took the resistor out, and of course, if I connect the leads, it'll just show me close to 0 ohms. It'll be basically the only left resistance that's left is the wires of the test leads themselves, the resistance there. Okay, but yeah, there you do. Just switch it to ohms and you're done, and you just have your leads in these two positions in case you needed a reminder of how to measure resistance. So I measured my resistor, and there it is, 10 ohms, and now I'm going to put it on the board, you know, wherever. Just pick a spot. And of course, don't put it on the same node. I mean, if you needed that review, I mean, obviously, I think you know by now, putting it on somewhere like across the same node, you'll just short it out. So don't do that. Just get it on the board here. And then, before I put my ohm meter away, I did remember maybe I could check my lamp and just see what its cold resist. This will be cold resistance, remember. It's not on. Can I measure the hot resistance of a lamp, like when it's burning? Can I do that with an ohm meter? If you remember, you cannot. Because why? Because an ohm meter can't go into a powered circuit, for one thing, and it also needs to be measuring the component in isolation. Can't be measuring other things around the component. So, but here I have my my lamp at what, 20? I'll say 26 ohms for that. Incidentally, that's also how you would check to see if your lamp is good or not. If it's burned out, that means the little metal filament inside just burned up, and there would be an open there. So if you were measuring your cold resistance of your lamp and you saw overload on your ohm meter, that just means there's an open. The filament's burned up. Same way you would check a fuse. In fact, the lamp is very similar to a fuse, isn't it? It's inside a glass vial. It's a thin metal piece of metal where if too much current goes through it, it burns open. Very much the same thing. There's examples where people even use lamps for fuses. Okay, let me put down 26 ohms, but I got to remember that's the cold resistance. So, oh, I don't know. Where do I want to notate that? Maybe up here somewhere. R lamp cold. Just in case I need that information later. 26 ohms. Okay, now I think I can switch away from my ohm meter. I got those things done. All right, let's finish wiring this up. So I have that wire. I have this wire yet to put in place, right? I got to connect the other side of the lamp to one side of the resistor. I'm just using yellow jumpers. That helps remind me that that's in fact the lamp. So little tricks like that make it easy on the eyes. The other side of the resistor then comes all the way back to the negative side of the power supply. So I'll use black for that. It's a good color for that. And here is the low side. Okay, so let's see if you can see those connections. Again, a little bit like spaghetti because we are using the long jumpers. If you wanted to really make this easy on the eyes, yeah, you could use you could cut your own and color code. If you were going to make a little demonstration circuit for somebody, that might be a really nice thing to do to really see things easily. But there they are, and you can double check all your connections. Series 8ing, power, positive power to the push button, then to the lamp, then to the resistor, then to the other side of the voltage. Remember, my 3 volts that I have is on the bottom and top rails. Once you've wired it and double checked your wiring, time to test it out, right? Should work, pretty confident, unless I missed by a node. I always reserve that possibility. Like these nodes, especially, I'm thinking, did I get those right at the push button? Because they're kind of hidden from you once you put the push button in place. Let's try it. We'll push the button and we won't panic. If it doesn't turn on, that doesn't make me think that some obscure event has occurred in the universe that prevents my circuit from working. I know it's a simple circuit, and so it's a simple mistake. So keep that in mind, especially when things get maybe a little more complex. It's never some cataclysmic event or some bizarre workings of the universe that are keeping your circuit from working. It's simple little mistakes, always. So you'd be off by a node is probably the most common mistake. Sometimes a wire fails and so on. All right, well, here we go. Okay, so all is well. The light's coming on. When I press the button, of course, I complete a path for current to flow. The current's pushed by this voltage here. Speaking of which, I'm kind of curious what that voltage is. So I've got my breadboard test leads, you know, with the little pins. Throw it to volts. Not there, right? That's AC volts, DC volts. There we go. Let me have a look. It doesn't matter where you look. I mean, yeah, maybe, you know, you might think I got to be right here. You don't. That's a little crowded, right? I can inspect the rail voltages, they'd call them, or call it, anywhere along the rails. This is all the same point electrically. So I'm going to hop on there, have a look. And I can see that I've got, what, 3.123 volts. And that is the no load voltage. In other words, I'm not putting a load on those batteries. I'm not asking for any current. I did not complete the circuit by pushing the push button. So that's the battery's ability. That's their voltage. That's the chemical reaction's ability with no current being asked. There's no work to be done. And so that's what that voltage is. So that's no load, or NL, but I'll write it out here. 3.123. And we did mention, and I mean, I'm only bringing these details up now because I think it helps to reinforce some stuff we'll get into later. But here, when I push the button, I'm asking for current now, and it does droop a little bit. The voltage is now down to 3.092. Okay, and that's kind of a moving target. That's with the lamp. With a load, it's not necessarily a real heavy load, but that's the load we've got. And again, that's more of a curiosity for now, but it does explain some things down the road that we get into. And they would, that'll be a topic called source resistance. So let's mark this. This would be our source here, right? Those voltages there. And what else can I investigate? Well, we could see what voltage the lamp's getting. I guess that would be a good thing to investigate. So again, remember, when you have your voltmeter in play, you can poke around wherever you want. It's high impedance. It's not going to get anything in trouble. It's a little hard. We're running out of node space for this lamp, aren't we? Do you believe me if I show you that we can get right in there, right here and here? I have the lamp right on those two nodes. So let me just get in there. It's tight, but we can do it. So inspect that, but you should be right across the lamp. And let's make a little space here for lamp voltages that we're curious. So we're just investigating with our meter now. So I mean, it gives you a little practice with the DMM, right? Which we definitely need. Let's see what the lamp looks like. Well, when the button's not pressed, I'm not getting any voltage, so that's one thing I'm measuring right now, right? When it's off, I get 0 volts. And that's kind of obvious probably, I think. I mean, look, if it wasn't 0 volts, it'd be voltage across it, it'd be pushing current through it, and so on. Let's try pushing the button and see what the voltage is that across the lamp then. How much voltage do we get there? Oops, I'm blocking that. Let me get out of the shadows here. So my lamp's on, if you can see, 2.933. 2.933. And that's when it's on. Okay. All right, so far, let's look at our schematic here. Maybe that's a good way to review what we've done so far, right? So far we've looked at this voltage with the button not pressed and pressed, so off and on. Then I guess we were over here looking at the lamp with the button not pressed and pressed, off and on. Might as well have a look at the voltage across the 10 ohm resistor with the button off and on. So let's do that next. Again, with the voltmeter, you can just poke around. You can investigate any 2 points that you want. And I am going to be right across that 10 ohm resistor now and look at the voltages that result from pressing the button or not. So when the button is not pressed, again, probably not a surprise, but here's my resistor. Let's get that recorded. And it's big surprise. There's no voltage across it when the button is not pressed. And when I press the button, let's see what happens. Current is flowing now when I press the button, which means as current runs into that resistance, there will be some backed up charge at the entrance to that resistance as soon as it hits it. Think of a river flowing and there's a rock in the middle of the stream, in the middle of the river. You know, when the water hits that obstacle, it tends to back up. You will see water backed up at the entrance to any obstacle, which is what the resistance is. So there's a difference in pressure from one side to the other. There's positive pressure backed up here at the entrance to that resistor, and then on the downside, on the downstream side, it's lower pressure. So, all right, and that difference in pressure, but difference in voltage is what we would call it, is 154.6 millivolts. Don't forget the millivolts. Don't miss milli here. Oh, what was that again? Whoops. Let's do it. Yep. Takes a little while for the meter to settle in. And again, it might be a moving target. Batteries might be running down a little bit. I'm just going to call it 155 millivolts. Okay, so let's get that recorded. That's, of course, when the circuit is on, when I'm pressing the button. And there is one more component that we did not investigate yet with the voltmeter. You might not think of doing it, but it is something you do as a technician, and that is the push button itself. So let's get our voltmeter across the push button. Okay. Again, just make sure you get on the same nose. Now again, I know it's a tight spot there, but we'll see what we can find out about this. So we've got our voltmeter sitting right across the push button contacts. What would you predict when we press that push button or not? Well, I guess we're already seeing something, aren't we? With the push button, it's not being pressed, so it's off. And look what you get for the push button, which is the switch of the circuit, right? It's what's switching the circuit. So I'm getting voltage when it's off. And this is something that I think is really important to get comfortable with. Sometimes if people aren't really thinking about it, if they just maybe their first thought is, well, when it's off, I won't have any voltage across the switch. It's the opposite. When a switch is off or open here, like we see here with this push button, let me get this wire out of the way. It will have all the voltage across it when it's open. And think about it. It makes sense, right? All this pressure has nowhere to go. It all piles up. On either side of here, you'll have all of the voltage because all the pressure comes here, and there's no place for it to start evening out or equalizing. So you will always have all of your voltage across an open if there's an open in a simple series circuit like this. So hopefully that makes sense. You need that understanding so that you're not being too simplistic in your thinking and thinking that, well, it's off, so I won't have any voltage across my switch. My meter again. And that will, of course, lead you down the wrong path in your reasoning. So when you check a switch in a circuit, if it's working properly when the switch is off, that's when you see voltage across it. And when it's on, what do you think you should see then? Remember this little sort of mind's eye trick with our I'll just squeeze it in here somewhere, with our water analogy. How much voltage can you have across 0 ohms, I guess is what I'm sort of trying to picture. So if I have a path and there's really no, I'll get that up on where you can see it. If I have really no resistance, just represented by that dotted line, can you even establish a difference in water level? Remember, that's like the 0 ohm thing, that dotted line. And the answer is no. You can't establish any difference in water level if there's no resistance between the 2 points. And when you press that, it's 2 pieces of metal being connected together. So you shouldn't be able to establish any difference in voltage between those 2 points. Now, how perfect are the switch contacts? Well, if they're gold plated, they're probably pretty good. But there might be a tiny bit of resistance. And so if whatever little bit of voltage you do see across a switch tells you how good or bad the contacts are, and that's a good way to test switch contacts. They should not have voltage across them. They should be a nice 0 ohm, 2 pieces of polished metal coming together. But as they degrade, they will have some resistance, and then you'll start to see some voltage across even a switch that's turned on. So let's go ahead and press that button. Let's see what we have with our push button. So I'm pressing it. You can see the light lights up. And in fact, yeah, it looks, again, how accurate is our DMM. So it's essentially 0, isn't it? I mean, if you want to really go down to millivolts, 0.7 millivolts, which would be what? 700 microvolts, right? So that just shows you how good the contacts are. I'm going to put here, because I don't really want to, microvolts, I don't really need to go there, but it's pretty close to 0 volts when it's on. And again, just always remember that, you won't have voltage across your switch when it's on. And I think it also makes sense, hopefully, to you, because the voltage when you press the button should not be across the button. Turning the lamp on means the voltage is now over here across your lamp and across your resistor as well. But that's the idea. So I think what we'll do is let's take all of these voltages that we kind of investigated and let's put them like where we can see them on the circuit, just maybe to wrap this little exercise up. All right, so I've written all the voltages that we've investigated with our voltmeter onto the schematic itself. Here's a little note: the number, the bottom number, is when the push button is off, and then the top number is when it's on. So let's have a look. We've got 3.12 volts from here to here. That's our source. In the off condition, it's 3.12 volts. The push button has all of that 3.12 volts across itself, because all of the voltage will be across the open. All the pressure is here. It's just like a dam, that's not allowing any water to flow. It's all dammed up. There's no way for it to get from here to here, so all the pressure will be across that open. It's essentially infinite resistance. It'll claim all the pressure, all the voltage. So there it is. And of course, since the open gets all the voltage, there is nothing for the other components. They get 0. It's all here. All the pressure is across here. You can also think of that as just Ohm's law. Think of it this way. With an open, no current can flow, right? You've got nothing. No current can flow. If you have no current, how can you have voltage, right? Because remember, V equals IR. And if I is 0, it doesn't matter what R is, you can't have any voltage. Yeah. And you might, so that explains, of course, an easy Ohm's law explanation for why you have 0 volts across here. There's no current running through it. How could you have any voltage? It gets, the math gets a little tougher. It's hard to handle this scenario, isn't it? But it's infinite ohms. So what is 0 times infinity? Our math can't quite do that, can it? Now, when you push the push button down, things change, of course. One little thing that, again, I don't care so much about it right now, but it's there, it happens. As soon as you start demanding current from those batteries, their voltage that they can provide drops a little bit. So we now have 3.09 volts from here to here. Notice none of that voltage, essentially, I mean, yes, we saw, I think, like 7 microvolts. Not going to worry about that. Essentially no voltage across here, but of course it makes sense because when you push this down, you're connecting 2 pieces of metal, approximately 0 ohms. How can you have voltage across 0 ohms? You can't. You won't. There's no pressure buildup when there's no resistance to flow, no restriction there, so no pressure there. There's restrictions here and here, and so as current flows, there will be pressure across this restriction and pressure across this restriction. When we get to series circuit analysis and the actual theory that we have to actually get down pat, that's one of the things that we'll have in our heads, that voltage does divide up, or pressure does divide up across resistances in series. And probably not surprising, hopefully a little bit intuitive, you'll find out that the greater resistances or the greater restrictions get more pressure across them. Because, hey, current's having a tougher time flowing there, it will have more pressure then as it tries to get through those spots. More pressure will develop across there. Lots of ways to look at it. Ohm's Law, of course, can keep you straight too. So even if you don't feel like totally playing with it in your head as far as visualization or understanding with rotating the concepts as much, although that's a good exercise, Ohm's Law will never fail you. You can just straight up apply Ohm's Law. But we'll get to that. But here we have the button pressed. So 0 ohms. Again, now we do have that same thing with 0 ohms. How can you have any voltage? You can't. 0 volts gets across here. That's this number up here. So then you're left with the 3.09. The switch gets none of it. Again, remember, when you're checking a switch, don't be surprised by that. You know, you might, I know technicians that have put their voltmeter across a switch and said, well, there's your problem. The switch is on and I don't have any voltage. But of course you will not have any voltage across the switch. So when you're checking across the switch, now they might, now if you put, again, sidebar, we'll get into the differences, different types of voltages. That's across the switch. If you check the voltage at this point with reference to here, that's another test point. And don't want to wrinkle our example here yet, but those would be circuit voltages if you have a circuit common and you check here, here, and here with reference to the common. We're looking at component voltages in this exercise, which is the difference in voltage across a component. We got 3.09 with the button pressed, 0 volts across this one, and we've got now we do have some voltage across our lamp, but of course, because current's flowing. So let me get that current in there so you can visualize. As soon as you press this button, it completes that path and allows current to flow. And we've got it. And in fact, we have 2.93 volts across the lamp, and we have 155 millivolts across the resistor when things are on. So again, this little key will help you if you didn't make sense of my numbers here. But the off situation is this bottom number, and then the on situation is the top number here. And you see when it's on, most of the voltage falls across the lamp, and some voltage though does fall across my resistor. I've chosen a 10 ohm resistor for this example. What I'd like you to do is try some different resistor values here and compare with classmates. You can get on chat or even do a live call, but compare, try some different ones, and if you need to check to see if you're right, best thing you can do is maybe call up a classmate or chat with them and say, hey, when you put, you know, I don't know, whatever resistor you want to put there, you could try putting something much higher. You probably don't want to, if you go too high, you'll get such a small current, it'll be hard to measure, but you could try hundreds of ohms. You could try like, you know, 47 ohms is a standard value, but you could try some different ones and challenge yourself to do these measurements. It gives you practice with your ohm meter. I mean, your DMM gives you practice with ohms, volts, and current. We'll do current in a minute. But that's my idea for you, that you can try some different value resistors and also maybe get a classmate to try it and compare notes, see if you get the same numbers. If you do, you're probably doing it right then. That happens out in the field too. So nice, you check with each other to double check yourself. Well, what else could we find out about this circuit? I mean, we checked our cold resistance and we checked this resistance, so we did a little ohm meter stuff. We did a lot of voltmeter stuff, and that's typical. That is the instrument of choice, a voltmeter to investigate a circuit. We did not look at current yet. So of course we can get some practice with our ammeter. And before we do that, I want to tell you that even though we didn't measure the current yet with our ammeter, we already know it. In fact, we know it better than what we'll know with our ammeter, because our ammeter is not perfect. It'll insert some resistance into the circuit. It's not a real expensive ammeter, so it's going to mess up the circuit even a little more than say a $300 meter would. So we know, we have to remember, we're gonna go ahead and put it on the milliamp scale, but with that, we're gonna add another 10 ohms into the circuit. So we won't be able to see what the actual current really is right now when I push this button. We won't be able to measure that current with our ammeter. We'll measure it, this current is hard to measure because we're gonna be inserting our ammeter with a 10 ohm. Like I say, with a more expensive meter, we could get around that. But I want to tell you, before we even practice a current measurement with our ammeter, which I want to do, it's important, I want to tell you that you already know the current, and you know a very accurate, measurement of that current using Ohm's Law right here. So this will actually tell us what the circuit current is. We have the voltage that we measured across a known resistance of 10 ohms. That resistance is in series in the same path as the lamp. So whatever is flowing through here is also flowing through here. So I know my lamp current. I know my resistor current, which will also be my lamp current, which will also be the current flowing through the push button when it's closed, and also the current that's being supplied by the source, by the batteries. Again, in this example, it's a simple series circuit. There's only one path, so there is only one current, and it's the same everywhere. And we've got it with Ohm's Law, and we've got it most accurately with Ohm's Law. So when you want to measure current in a circuit, yes, there are times you can use an ammeter, and there are ammeters that just measure the magnetic field that's being produced by the current. That's something we'll get into down the road, and so you don't have to insert it into the circuit. So that's another way to not mess up the circuit. Our ammeter, though, is not that type, and it's going to be inserted into the circuit, and since it's only a $50 meter, along with the ammeter comes 10 ohms. So we'll do that, but we have to keep in the back of our mind that that's going to mess us up a little bit, mess our circuit up. But here we are. Let's do the Ohm's Law. That is going to be the most accurate current that we've got in this. We measured current by measuring voltage across a known resistance. Let's do it. And that Ohm's Law calculation comes out to 15.5 milliamps. Remember what current is equal to, right? It's going to be voltage divided by resistance for Ohm's Law. And then you get this 15.5 milliamps. That is the circuit current flowing. There it is written out for you. V over R, that's I. That's how we got this. 155 millivolts divided by 10 ohms. We get that. Something else I wanted to mention, as voltage divides up around the circuit components, the pressure that divides up, it is true that those component voltages or pressures will always add up to the source pressure. Of course, it's pushing with a total push here, or there's a pressure here or a voltage here, and that gets that divides up according to the restrictions that it has throughout the series circuit. So you can double check that, of course. And of course, let's see. So what we're saying is that this this 3.09 volts, for example, when it's on, when the circuit's on. None of it gets across the switch, but the 2.93 across the lamp, and then the rest of it is the 155 millivolts across the resistor. So this plus this equals this. And I think if you do it, it comes up as like 3.085 volts. It's always hard to match exactly. It's a moving target with these batteries. Their voltages tend to fluctuate a little bit as the lamp's been on for more time or not. Yeah, they tend to run down a little. Let's get some practice with our ammeter. So remember how we do it. I mean, if you're going to use it to measure current, well, you got to be over here if you're going to use your DMM. So there's microamp scale, milliamp scale. That's the one we'll use for resolution. The 10 amp scale, it's there. It would be even less intrusive. I mean, you would only put maybe I forget what it was, a tenth of an ohm maybe only goes into the circuit with that scale. However, the resolution's so bad because we're down here at milliamps, and it would hardly register on the 10 amp scale. So, but to use the 10 amp scale, you'd bring this jack over here. We're going to leave it here where it is because that's where you'd leave it for microamps or milliamps. So I got it on the milliamp scale. Now remember, what is the most important thing when you're going to do a current measurement with your ammeter? I mean, it has to go in series. Do not try to look at the lamp's current by doing this, right? I know this is review, but it's important review. What's going to happen there? You're just going to short the lamp out. All the current's going to run around the lamp. What's really bad is if we didn't have this resistor here, if we just had a simple circuit with a push button and a lamp, what would happen as soon as if you had your ammeter mistakenly connected like a voltmeter, what happens when you push the button if this resistor wasn't here? We'll pretend it's just a simpler circuit. Poof, you just blew the fuse in your ammeter because it's a dead short. You've got your 3 volts. The switch is like the piece of metal, connects it straight across your low resistance of your ammeter. High current is what happens and blows your fuse. Yeah. So of course, that's not how we do it. You have to open up the circuit, put your ammeter into the circuit. It does not matter where. So I mean, I could open up the circuit here, and then I could reconnect the circuit using my ammeter, which is essentially putting the ammeter into the path. And I have to do that because I need to get the current measured as it flows through my meter. That's the only way I'm going to be able to measure it. And it doesn't matter where. Current's the same everywhere. That's another thing we had mentioned, and don't worry, we'll be emphasizing that more in upcoming sessions. But so the meter could go there. I mean, it could go here. I could open it up there and put it in. I could open it up here and put it in. Here, it doesn't matter. So we'll pick a spot wherever we want. I'll just put it on the low side. That seems like a convenient spot. Look, I'm going to pull this wire out right here. If you can see, if I can show it to you. Look at this common one, this one that brought the connection down to the low side, the 0 volt side, and then I'm going to reconnect with my ammeter just like that. And I'll get an ammeter measurement now, and I won't, instead of blowing my fuse, right? I mean, sometimes those are the two things that happen. You get a measurement or you blow your fuse. All right, let's push this button, and there's our lamp. And on our screen of our ammeter, we see, don't miss the milli, right? The milli's showing up right there. It's DC. We'll talk about that in the next course, DC versus AC. 15.03 milliamps. 15.03 milliamps. So with the ammeter measurement, we've gotten the 15.03 milliamps. And yes, it's a little bit less because we've inserted that extra 10 ohms or something close to that with our meter. This I would probably put down here, I'm running out of room here. This is getting crowded, but that would be my measured value for current. This would be calculated. You want to keep that stuff straight, This was calculated from a measured voltage. So you want to always notate those things. Calculated, right? And it's not a good example of organization, is it? I just typically running as always running out of room here. But this is the kind of notation you want for yourself when you're looking back at your work. You need to be able to remember, how you did what you did, why, and it helps you explain. Why is this current a little lower than that one? That's the measured value with the extra 10 ohms. Might not be exactly 10 ohms, but it's going to be in that realm that your meter added into the circuit. And you don't always, have to split hairs. We're not going to always split hairs like that. Sometimes it's necessary because you might need it to explain something, but in either case, 15 milliamps might be the valid answer. So, because it's going to vary anyway a little bit as the batteries, wear out a little and so on. So, we're not always splitting hairs. I'm just using this extra detail to help you understand your meter a little more. But in many cases, 15 milliamps is a fine answer, however you found it. So I think we've done pretty well at characterizing the circuit. Probably just one last thing. I am looking at that lamp and I'm saying to myself, I got the cold resistance of 26 ohms up here, with the ohm meter. And I'm thinking I can squeeze one more detail out of this whole exercise, and that would be the resistance of the lamp, the hot resistance, right? I got the cold resistance there, but can you remember when it's actually on, the filament, that little piece of metal in there, is burning hot, and when metal is hot, its resistance goes up with temperature. It's got that positive temperature coefficient. Let's calculate it. Where do we find the numbers? Just wherever you can find a chance to do Ohm's Law. Don't turn it down, right? Might as well do it. I do see I have, when it's on, when the lamp is on, I see I've got a voltage that's across it of 2.93 volts. So if that's the voltage difference from this point to this point, and I have a current of 15.5 milliamps running down through it. Now I'm going to use this one, not this one. Because this is the more accurate one. The 15.5, if I care, or I could just use 15 milliamps and that'd be close enough. I don't always have to get that detailed, but good for the exercise. So if I have a choice, I'm picking this one. It's the more accurate one. The ammeter is not influencing the circuit with its resistance. So I'm putting that one. So there's my Ohm's Law right there, right? If I know voltage and current, and I do, voltage across the lamp and the current running through it, I know what its resistance is at that moment when it's burning. I cannot get that resistance with my ohm meter. I can't put my ohm meter on a live circuit. I also need to isolate whatever I'm measuring, resistance wise anyway. So 2 reasons I can think of why I can't get on there with an ohm meter, but I don't need to. I got there with a voltmeter, and I got this with a voltmeter and an ohm meter previously on that 10 ohms, right? So you see the steps. This example I'm hoping gives you practice with your DMM, but it really also gives you practice with the mind of a technician. Ohm's Law, and I'll have it. Let's do it. And when we do it, 189 ohms, big difference, right? Hot resistance, but it's burning hot, that metal inside there. And there's 26 ohms when it's cold. And again, the 189 right from these 2 numbers using Ohm's Law. So a lot of concepts in there, and I love that it's a video. You can review it. Of course, you can pause it and go step by step, build your own simple circuit. Like I said, maybe you try this one with the 10 ohm resistor, but then try some other values in there. You could try 47 ohm. You could try whatever resistors you have in your box. You could keep working up through into several hundred ohms. And you'll see as you add resistance, of course, shouldn't be a surprise to you, right? You should get less and less current. If you go higher than 10 ohms, this current's going to go down. Now, it's going to be kind of hard to predict because you have a lamp. So when you try other values, you might increase this resistance, which will decrease that current in a way. It'll also make the lamp burn less bright, which means it won't be as hot, which means this resistance is going to come down. So it's kind of going to be an interesting one. I use it on purpose for that reason, because it's pretty hard to calculate what the theoretical prediction would be. You can't really, because this is sort of the thing that is hard to know. Again, you're going to bring resistance up here, which will lower current, which will bring resistance down here. And so you'll constantly be playing with those variables. Just try some different resistors and compare notes with each other. That's my idea for you. So experiment, and it's a good exercise, I think, because it forces you to do measurements. You know, it's more interesting too that way. If you didn't have this lamp, like we said, trickier than you ever thought, you know, that little lamp there. If you didn't have that, we can still do some exercises, and maybe you want to. You could predict theoretically very easily, because it's just fixed resistance that doesn't change. But this will be a good challenge for you, and lots of practice with your DMM. I think because of that tricky little lamp. So try different resistances. You'll get different currents, and you'll get different hot resistances out of it, and it'll keep you honest. You'll really have to measure with your DMM. There's no theoretical way to get around it. You have to poke around with your voltmeter and then compare notes with each other. When you do the experiments, you know, get a nice big sheet of paper where you aren't running into what I run into here, trying to squeeze it all in the camera frame. This is not the organization I would do if I had a nice open piece of paper with a pencil or an Excel spreadsheet. You know, that's really nice, isn't it? So, but however you do it, I'm not saying this is your best example of how to be organized. You can just have a little more space for yourself. Maybe that's something we'll do. Maybe put it on an Excel spreadsheet. That'll be easier to pass around, wouldn't it? So we'll stop the video here. Long enough, getting close to that hour again. I hope that provided you with some good review. I know a lot of it is review. It's also a lot of preview though, which because very soon we'll be getting right into series circuit analysis. So I'm hoping this helps pave the way for our understanding of series circuits. And also, of course, I'm sure it gave you practice, or gives you practice with your DMMs. So those are some goals. I put this on wattage, right? I've got it, voltage and current. So my lamp, when it's on, is burning at 45.4 milliwatts. I could get the wattage of my resistor also if I want, voltage and current. So might be a couple other things that we're able to calculate, but we'll call it there.